So now we're into the last chapter, and there's only a few sections that we're going to cover in here. And this first one is really back to when we first started talking about factoring. So we're going to look at that again, just factoring problems. And then all those problems that were not factorable, we're going to look at the quadratic formula. And the thing about the quadratic formula is whether it's factorable or not, we can always use that formula. So for those of you who hate factoring, this is just one other thing that you can use. All right, so the standard form always has to be set equal to 0, ax squared plus bx plus c, and we wanted our a term to be positive. So it says greater than 1, but really it's greater than 0. When we write the quadratic equation in standard form, we want to just identify what a, b, and c are. So for this first one, the coefficient of x squared is 1, so a is equal to 1. B, the coefficient of x, is 3. And c is equal to a negative 2. It was already set equal to 0, so we didn't have to do anything, just read it right off. The second one is not in standard form, so I need to move that 6 over first. And then there's another problem with this. The coefficient of x squared is negative. So first I'm just going to write it as negative 3x squared plus 2x minus 6 equals 0. And then I'm going to divide everything by negative 1 because that coefficient has to be positive. So when I divide everything out by negative 1, I end up with 3x squared minus 2x plus 6 is equal to 0. And now I can see that my a is equal to 3, my b is equal to a negative 2, and my c is equal to 6. So if not in standard form, you have to put it in standard form first. 3 is also not in standard form. So I have to move that 4 over. I'm going to rewrite it as 4x squared minus 4 is equal to 0. So in this case, my a term is 4. There is no x there, right? So my b term is equal to 0. And my c term is equal to a negative 4. We go down to number 4, and we have the same problem. I need to get it equal to 0 first, so we have to add 5x. And I get x squared plus 5x is equal to 0. So a is equal to 1, b is equal to 5, and this time c has to be equal to 0 because there is no constant there. 5, because this is negative, this time I'm going to move everything to the left. So I'm going to add 5x squared. I'm going to subtract x so I can get it set equal to 0. So my a term is 5, my b term is negative 1, and my c term is 16. And then finally for number 6, I'm going to move the x squared over, so I get 0 equals x squared plus 2x minus 1. A is 1, b is 2, and c is negative 1. So these a's, b's, and c's we're going to use a lot in the next couple of sections because we're going to be looking at parabolas and the quadratic formula, and a, b, and c has meaning to all of it. So it's important to be able to identify those. So we want to solve the quadratic equation using the techniques that we learned in chapter 6. So it just has to be set equal to 0, factor it, and then take each factor and set it equal to 0. Number 1, I'm going to subtract the 4x and the 5 from both sides. And then that factors to x minus 5 times x plus 1. Then we set each of those factors equal to 0 and solve for x. So I get 5 and a negative 1. Number 2, I'm going to add 4 to both sides. So I get 2x squared plus 6x plus 4 is equal to 0. They have a common factor, so I'm just going to divide 2 out of everything. We get x squared plus 3x plus 2 is equal to 0. Just makes it a little bit easier to factor. So we're going to factor at x plus 1 times x plus 2. And then again, set each factor equal to 0. And my two solutions are a -1 and a -2. Number 3. I'm going to move the 7x over. Now, even though for that last problem I can divide out of 2, I can't do that with a variable. I can do it with a constant. Any constant, I can just divide it out. But if I divide out a variable, I'm actually going to eliminate one of my solutions. So I can't just divide out the x. I need to factor. So I'm going to pull that x out. And then set each of these equal to 0. So x equals 0, which I would have lost if I just divided it out. And 5x minus 7 is equal to 0. So I'm going to add 7 to both sides. And then divide by 5. So my solutions are 0 and 7/5. Number 4, I'm going to factor because it's in the process it's telling me to factor. But when we were doing radicals, we also know that we could just take the square root of both sides. But I'm going to subtract 16. And then that's the difference of two perfect squares. So I have x minus 4 equal to 0 and x plus 4 equal to 0. Solve each one separately, and my solutions are positive and a -4. So those are all factorable, but like I said, not everything is going to be factorable, which doesn't mean there's not a solution. It just means it's not factorable. So the quadratic formula actually lets us know for sure whether it's just, not factorable to a nice integer or fraction or something like that, or if it really is no solution to it. So standard form, ax squared plus bx plus c equals 0, have to have that. And here's our quadratic formula. So the opposite of the b term, plus or minus, and inside the radical, b squared minus 4 times a times c term, all over 2 times the a term. So here's an example. We have 2x squared plus 3x minus 5. So the first thing you want to do is to identify your a, b, and c so you know where to plug stuff in when you're going back to the quadratic formula. A is 2, b is 3, c is -5. So we get the opposite of the b term, plus or minus the b term squared, so 3 squared minus 4, that 4 is always there, times the a term, which was 2, times the c term, which is -5, all over 2 times the a term. So you have to simplify inside that radical. 3 squared is 9, and then minus 4 times 2 times -5 gives me a 40. So we add those together, and now we're at 49 in the radical. Well, this happens to be a perfect square, which tells me it was factorable to begin with. And I get two solutions, -3 plus or minus 7 over 4. So we're going to write it two separate ways. -3 plus 7 over 4, which gives us 4 over 4, which is 1. And -3 minus 7 over 4, which is -10 over 4, and that reduces to a -5/2. Alright, so we're going to go through a couple of problems. This first one, a is 1, b is -3, and c is -10. It was already in standard form, so I didn't have to do anything with that. So I get the opposite of b, plus or minus the square root of b squared minus 4 times 1, which is the a term, times -10, which is the c term, all over 2 times 1. So that's what I need to simplify. I get 3 plus or minus, -3 squared is 9, minus 4 times 1 times negative 10 is going to give me a positive 40 over 2. So 40 plus 9 is 49. Again, that's just the perfect square. So I end up with 3 plus or minus 7 over 2, which is two different answers. One is 3 plus 7 over 2, and one is 3 minus 7 over 2. So this gives me 10 over 2, which is 5. This gives me a negative 4 over 2, which is negative 2. So those are our two solutions. For the second example, it's not equal to 0, so I have to do that first. Put it in standard form and identify my A, B, and C. So negative 4 plus or minus 4 squared minus 4 times 1 times negative 7 all over 2 times 1. So I get 16 plus 28 in there over 2. So I don't have a nice perfect square that I did before, but again, remember what we did in the last section with radicals, we can break them down. So I get negative 4 plus or minus square root of 44 all over 2. And I like to do mine on the side. So 44 is 4 times 11, which is 2 square roots of 11. So I'm going to plug that in. And then lastly, because all three of these pieces that are outside the radical have a common factor, I can reduce it. 2 goes into 2 once, 2 goes into 4 twice, and then this 2 goes into 2 once. So I end up with, my final answer is negative 2 plus or minus square root of 11. Right? Because that became a 1 and that became a 1 down there. And if you want to write it two separate answers, it's negative 2 plus the square root of 11 and negative 2 minus the square root of 11.